Hi, now let's continue with applications of sequence models. So sequence models are particularly important with natural language and text. That's quite logical because natural language and text are, they're very easily viewed as a sequence. Language and text correspond to symbolic data, right? So a word is a symbol, a letter is a symbol, and it's important to be aware that for symbolic type of data, input representations are typically the form of one-hot vectors. What is a one-hot vector? It's a vector which has everything in its entries as zeros, except for the active dimension. So this means that the number of dimensions of our one-hot vector will be the same as the number of dimensions in our vocabulary. So for instance, in this example here, we've got 1, 2, 3, 4, 5, 6, 7, 8 possible words. This means that we're going to have a 8-dimensional one-hot vector, and the hot vector of each word is basically a vector of zeros, except for the location, that corresponds to the word itself, which is then lends itself to a 1 in the vector. For instance, then if I have 12 words in a sequence, then I would create 12 one-hot vectors, one per word, and each one-hot vector would be a vector of zeros, except for one dimension that is 1, and it depends on the location of that word in our vocabulary. After the one-hot vectors are applied, are determined, we can apply an embedding, for instance, word2vec or glove. So why do we make ourselves more complicated like that and we use one-hot vectors? Why not use indices instead? So for instance, the word I is the first in my vocabulary, the word am is the second in my vocabulary, the word James and Maguire is the fourth and the seventh word in my vocabulary. Well, the thing is that if we use the indices like that, so the natural numbers as a representation for our word, we are introducing an artificial bias, because suddenly some words become closer to each other for no apparent reason other than the random location that they have in our vocabulary. So in this example here, two words like am and Maguire always, or I and am, will always have the same distance from each other, square root of 2. However, with the index representation, these pairs of words will have different distance with each other. So am from Maguire will have a distance of 5, whereas I and am will have a distance of 1. And although having different distances is okay, in fact that's what the word embeddings like glove and word2vec do, we don't want to have artificial distances. So there is no reason why am and Maguire should be 5 times further away than I and am, right? So we have to make sure that at least at the raw level, like raw data level, our input representations are equidistant, and this is what we can achieve with one-hot vectors. Now, some applications, and I'm going to go here only, like on a very superficial level, are the following. We've got text generation, so you can use LSTMs or recurrent networks to decompose the text sequence and then learn how to generate new ones. Well, given a starting word, you sample one new word at a time, and then you unroll until you reach the end of sentence symbol. As simple as that. Very important, very popular, especially in the last 5-6 years, have been the encoder-decoder architectures. For instance, for machine translation, we could have one source phrase in one language. For instance, today the weather is good, and what we can do is we can use an LSTM to basically encode this sentence. Our encoding of the sentence will be the final state. So here we're going to have 1, 2, 3, 4, 5, 6 with the end of sentence symbol. So our encoding here will be the 6th state, right? And then we take this, so we take this 6th state is computed at this location, right? And then we pass this 6th state to a new LSTM, a decoder LSTM, which learns to generate now a new sequence that matches with good translations. So then we're measuring the probability of or the likelihood of the translation given the past encoding from the source language. What is interesting is that we can generalize this concept such that our encoder doesn't encode sentences anymore. We can also use it to encode pictures. In that case, our encoder is a convnet whose state, for instance, the last convolutional layer or the first fully connected layer, whatever, that's a choice, is input to a decoder LSTM, and then the decoder LSTM learns to translate the image. Then we've got image captioning. As simple as that. The architecture is actually very similar to machine translation. We can also have here very cool demos of image captioning. And now what is interesting with image captioning is that it tends to return rather, I would call it biased captions, right? So it returns sentences that are found mostly on our training data. What is interesting is that the image captioning can similarly be changed to support question answering. So then you have an encoder for your question and you've got a decoder for your answer, or you can have even a question answering given image. So your encoder could encode the question, and your encoder, another encoder, you can encode the image, and these two are input become input to a decoder LSTM, which learns to generate an answer. So this was it for today's lecture. We discussed about what kind of inductive bias do we need so that we can modify our neural networks to work well with sequences. We have discussed backpropagation through time as well as the improved version of recurrent neural networks, that is LSTMs and variants. We have discussed attention and transformers, and attention neural networks and transformers, and we also covered a few applications of sequence models. Thank you.